Okay, this is my first live stream. I'm just gonna read this for a second, just momentarily. Okay, it just disappeared. Okay. What I was talking about is what's on my screen right now. Okay, moderation, help everyone feel safe. No. Choose who can participate, send it away, hide with people. Okay, there's not gonna be any people. Realistically speaking, first live stream, it's been one day. Okay, it's been one day. You know, it would be very unrealistic to assume that there's going to be viewers. Very unrealistic. So I'm not expecting viewers. Okay. What I'm hoping though is that the live stream records and then uploads the what I'm like recording right now straight away, because my Wi-Fi, the internet that I have, is terrible. It's terrible. So it took like ages to just upload that video. And yeah, I don't really want that to happen again. So I'll just live stream this. Okay, so we are going through the 2023 paper 2 past external exam today. Hopefully it doesn't take too long, but it should be alright. Yeah. I'll try my best to explain things. I don't think I explained things to the best of my ability yesterday. But yeah, okay. Oh, this is pretty cool though, the user interface. Wow. Chat rate. I don't know what that means. Yeah, I don't know what that means. Okay. Either way, this is not relevant, really. This is not relevant. What's relevant, however, is what we are doing today. Okay. What is this? Look at this. Okay. I have it already prepared, Oh, look at me. Oh, I'm so prepared. Okay. Question 1, 3 marks. A described question. Okay, in my previous video, I did say I don't like described questions. And fair enough, because I think I didn't get full marks on that question. I'm not very good at it. Okay, what is relativistic travel? So, okay, let's read the question. Describe the effects of relativistic travel on an object. Relativistic travel is it's approaching velocities close to the speed of light. And we know the speed of light to be a constant that's given on the formula sheet. I think it's 3 times 10 to the 8 meters per second. Now we can go here to our formula sheet, hopefully. Yeah, see, this is exactly what I meant by not good Wi-Fi. I can't even load the formula sheet like pretty quickly. It should be given somewhat. Yeah, it is given here, as we can see right here. Speed of light in vacuum, c equals 3 times 10 to the 8 meters per second. Okay, great. But that's not really relevant. Like, in terms of the question, it's not as relevant. It is, but it's not required, I'm assuming. Describe the effects. Okay, so special relativity. This relates to special relativity. 3 marks, so it's looking for 3 key points toward those marks, The teachers, the markers would be looking for 3 points to award you marks. It could be that you describe relativistic, you define what relativistic travel is. So I'm not going to write down a response. I'm just verbally describing my response. I'm just stating the key points that are in an exam I would write. But obviously, I feel like in terms of practice, understanding and being aware of the key points that are required is probably much more beneficial than me just writing the points. Because if I can actually think about the points and get the points correct, I can probably write them down in an exam situation. So that's, yeah. Okay, so relativistic travel is basically, when an object is moving at a speed close to the speed of light, right? Which then, if we go over to our formulas, okay, 3 marks, and well, there's 3 formulas associated with special relativity and relativistic speed especially. The effects of relativistic speed are more prominent than if the object were to have non-relativistic speeds. Okay, so according to the Lorentz factor, which is like 1 over square root of 1 minus b squared over c squared, which is just the square root part basically. As you increase the speeds to relativistic speeds, the object experiences time slower than observers that aren't in an inertial frame of reference to the moving object. So time slows down. Yeah. Okay, that's probably 1 mark. Length contraction. Okay, so when the object is moving at relativistic speed, the environment around it begins to contract due to light, kind of. I think it's because of the second postulate, or one of the postulates of special relativity, where the speed of light in a vacuum is a constant in all inertial frames of reference. In all inertial reference frames. Yeah. So I think that explains it. I think you don't need to go in super. A common theme I've seen is when I'm answering these describe or explain questions, not in the previous video, but just in the past, especially in the mock exam that I completed in my school, I tend to kind of over-explain things where I shouldn't, I don't need to, it's not necessary. And because of that, I think I'm kind of wasting time, first of all. I'm not being succinct, and I might be under a sense of false security, where, especially my biology teacher says this, rewriting the question it's a topic sentence gives you a false sense of security that you're actually writing, key things and you're getting awarded marks, but you're actually not, right? So I need to be succinct. I feel like I'm touching on really minuscule details that don't need to be addressed, Okay, so we've stated time dilation, we've stated length contraction. Why not just mention relativistic momentum? So as the object approaches relativistic velocities, the momentum becomes closer and closer, and it approaches infinity. As v approaches c, this part here, this fraction, gets closer and closer to 1. And under the square root, it's 1 minus that fraction. So when it gets closer to 1, the square root, what's beneath the square root is 0, and we know that if you divide something by 0, it's undefined. But if it's really close to 0, it's going to be a really large number. So that's what happens to the momentum. That's the effect. Okay, that took a excruciatingly long time to answer that question. Okay. I don't know if the live stream is actually working. It says YouTube is not responding. Okay, who cares? Who cares? Who cares? 11 minutes to explain that. Whew, not good. Not good. Not good. Okay. Question 2. 5 marks. In a frictionless system, object A rests on an inclined plane, object B, so it's stationary. So then force, we should be thinking immediately the net force is 0 from object A, and really we don't need to consider the perpendicular component of the forces. We'll just consider the parallel component, especially because the pulley is acting parallel, or based on the diagram it looks like it's parallel to the plane. Okay, object B is undergoing horizontal circular motion. Okay, so B is producing a force, centripetal force, and that centripetal force contributes to the net force of object A on the parallel component of the forces. Okay, so determine the speed of object B needed for object A to remain stationary. Okay, frictionless system. So there's no friction. Okay, let's first, we need to first get the resolve the vectors, the force vectors of object A into its perpendicular and parallel components. So let's do that. Let me just write down a diagram before I change the scene. The inclined plane is at 30 degrees. We have object A, it's 7 kilograms. Okay, here we go. I've changed the setup slightly, so I don't think my phone is more prone to falling. And I'm not sure if the audio is, you know, optimal, because I did review the footage, and there's a lot of frequent like audio glitches that happen distorts my voice a lot, and it when those distortions happen, you know, it's very difficult to actually make out what I'm saying. So hopefully that doesn't happen. Yeah, I won't know unless I review the footage, which is unfortunate. Yeah. A microphone would be a good investment, but we're just using my school laptop built-in microphone, so yeah. Let's just be grateful with what we have. Okay. Object A is 7 kilos. So in my previous video, I did say this. This angle, the angle of the slope, excuse me, the angle of the slope actually equals the angle at the top of this triangle here. So this part is 30 degrees as well. We don't really care about the perpendicular component for this question. So vertical vector that's going downwards is just the weight. And the weight is the hypotenuse of this right angle triangle. From this angle, so 30 degrees, the parallel component is actually the opposite side, so we're using sine, okay? So the force parallel equals W sine theta. Okay? We know that W is just force due to gravity, so mg. M is given, so it's 7 kilos. We times that by 9.8, which is gravity. And sine of 30 degrees is an exact value. Sine of 30 degrees is a half. We can use that. Okay, we can get our calculator. 7 times 9.8 divided by 2. Show that sine of 30 degrees is a half, yep. Okay, 34.3 newtons. So that's it. That's down the slope, but right now we know that the force due to object B is equivalent to this because it's said in the question that object A is stationary. So the forces are balanced, right? So the net force is 0. Which means that this parallel force is equal to the centripetal force produced by object B. Yeah. So this is F subscript C. Okay. So back to the question. Look back to the question. Okay, we're dealing with uniform circular motion. Yeah. It's explicitly stated in the question, horizontal circular motion. So we don't need to worry about any like uncertainties we might have. And also it's very clearly shown in the diagram that object B is traveling in a circular motion. Yeah. Okay. So we know the formula. Okay, 26 centimeters is the radius, 3 kilograms is the mass of B. Okay, we need to remember that, keep that in the back of our minds. Okay, so we know that centripetal force equals mv squared over r. Okay, what are we trying to work out? We're trying to work out the speed, which is v in this case. Okay, we know centripetal force is equal to the parallel component from the weight of object A, and we've worked that out to be 34.3. We can rearrange to isolate v squared. So to do that, we times by r on both sides, and then we divide by m, which is the mass of object B. So then that equals v squared. Okay, so v squared, we square root that part. So we just square root the left-hand side. Okay. And then we times it by the radius, which was 26 centimeters. And if we convert that to meters, we divide by 100, so it's 0.26. The mass was 3. Let me just verify all this information. Yep, it is. Okay, so that is the speed. Give us an answer of 1.724 meters per second. To two significant figures, so 1.7 should suffice as the answer to this question. I believe we should start going faster. It is 1.7. Okay. I don't seem to be able to... okay, now I can. Yep. 8-mark question. Pretty big question, but it doesn't seem too difficult. Okay. 3 charges are in a straight line as follows. Okay, we need to make sure we recognize that all these charges are positively charged, so they repel each other. Okay. Electric field strength at T. Okay. Well, if we navigate to our formula sheet, we know that electric field strength is here. E equals F over Q, otherwise known as 1 over 4 pi epsilon naught times the charge divided by R squared. Okay. I believe you can just sub in the net force, which is given on the diagram. So 2 positive 2, well, 2.8 over the charge of T. I think that's what Q represents in this case. Okay. So charge of T is 5 microcoulombs. Okay, so 2.8 times 5 microcoulombs, and obviously if you want to verify or check your prefixes, you can always navigate back to this, just like I said in the previous video. So it is micro for mu, which is 10 to the negative 6. (2.8) divided by 5 times 10 to the negative 6. Okay, so we get 5.6 times 10 to the 5 newtons per coulomb. Two significant figures. Okay. So that's part A done, I'm pretty sure. Now, what is the value of R? Okay. Let's think about it. This charge is not equivalent to this charge, I believe. I'm pretty sure they're not the same. Because here you're dividing by the charge that's not there. Okay. Given the net force is 2.8 newtons, it's to the left, which means that the charge at U is producing a stronger force than S. So, so that means that it's going to be the force due to charge U minus the force due to charge S. Okay. Since both formulas have the constant at the front, okay. So I'm distinguishing the charges by using subscripts, but lowercase q is going to be represent charge q. RU squared. Okay. So the subscripts are just going to represent the charge. Okay, yeah. Given that the constants are the same, we can just factor them out. Or better yet, we can just sub in the value. 9 times 10 to the 9. And then we multiply by the charge. We factor out the charge of t, since that's common. And then q, the charge of u over 2r. U to t is 2r, so we just sub in 2r as the distance, and we make sure we square that. Yeah. Okay. And then the charge due to s, and then we square that. Yeah. So it should look like that. And then we sub in the charges. Charge due to from t is just 5 times 10 to the negative 6. The charge from u is 40 times 10 to the negative 6. And then the charge due to s is actually the same as the charge of t. Okay, yeah. We can actually cancel out these scientific notation, or the multiples of 10. So we just use our index laws. 9 minus 6 is 3. And then 45, which is 9 times 5. Yep. Here, we need to get a common denominator. So what we can do is we can times this. Actually, no. We can just divide 4 from here and get 10. Yep. So I'm just simplifying it even without technology. Okay, so now we have a common denominator, so we can actually group the fractions. And then all this equals 2.8. So then r squared equals 45 times 5 times 10 to the negative 3 over 2.8. Okay. And this does not seem right, but we'll continue. 45 times 5 is 225 times 10 to the negative 3 over 2.8. Okay, and we put that under the square root to isolate r. Okay. I don't know if that's a correct answer. That does not seem reasonable, to be honest. Let's see. This might be the first time I get a legitimate question wrong. Okay, two significant figures. We'll put it in scientific notation. Okay, it's 2.8 times 10 to the negative 1 meters that we got. Oh, okay. Well, we got a correct answer. So we got, for the electric field strength, we got 5.6 times 10 to the 5, which is correct for part A. And then the procedure we used for part B was indeed correct, basically. And we did get the correct answer. Okay, nice. Currently, I'm using too much Wi-Fi. My brother is getting a bit angry. Yeah. Min Guitar says, "Bro, you're making the Wi-Fi slow." Whoops, whoops, my bad. Okay. Two objects. Oh, two objects on different planets experience different accelerations due to gravity. Determine which object has the greatest force acting on it. Show your working. This is a very simple question. That's why the difficulty is also C. You know, that's what Exam Insights just graded it, I suppose. Okay. Well, it's just Newton's second law, is it not? Yeah. Um, so what we do is we just times the mass with the acceleration due to gravity to get the force from gravity, force due to gravity. Yeah, F equals ma, which is Newton's second law. Okay, so 79 times 1.6. We get 126.4. For object B, it's 32 times 3.7. It's slightly less at 118.4. Here's the calculations. Just, yeah, in case. I'm not sure if it's very visible, but yep. Go to sleep one. It's past your bedtime. Okay. 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 The object with the greatest force acting on it would be object A because 126 is greater than 118. That's, yeah. Doesn't really matter what the direction is, it's just the force acting on it. You know, how great the force acting on it is. Yeah. Okay. Describe what happens when light is shone onto a metal surface in the context of the photoelectric effect. Okay, when light is incident on a metal surface, the energy of the photons excites the electrons in the metal. So the energy is transferred into the electrons, which can allow them, if they have specific discrete levels of energy, it can allow them to actually escape from the metallic surface and travel away from the surface. And this can only happen if the energy is great enough. So, since the metallic surface, since elements have their specific emission and absorption spectrum, photons with specific energy quantities can cause the electrons to go up stationary states due to the different quanta. And with enough energy, they can ionize and, like I said before, escape the metallic surface. In the context of the photoelectric effect, yeah, that I think I discussed it. You know, the quantization of the discrete energy levels, and how if the electrons absorb the specific photons with the required energy, they can move up the stationary states, and given enough energy, they can potentially ionize and become free. Okay, let's see. Light with energy equivalent to HF, so this is the sample response, has the ability to produce photoelectrons from a metallic surface. I did not say that. I didn't realize we'd have to actually relate it to the equation, the E equals HF equation. Okay, but that is technically the photoelectric effect equation, so it's kind of my fault. When the frequency of light is below the threshold frequency, the light will be reflected. Okay. When the frequency of light is above the threshold frequency, or yeah, specific key terms like threshold frequency, that's important. Photons will be absorbed, and photoelectrons with kinetic energy proportional to the excess energy will be released. The intensity of incident light is proportional to the number of photoelectrons for frequencies greater than threshold frequency. Ooh, yeah. Okay, I don't think I got many of those points. Like I'd say for the this one, but ooh, not a good response to be honest. 10-mark question. Okay. Um, ball is thrown with an initial velocity of 8 meters per second into a bucket as shown. So we're dealing with projectile motion. Okay. Calculate the time taken. Okay. So this part A question is kind of irrelevant to this diagram, except the angle, and that's about it. Yeah. Okay. 8 meters per second and 50 degrees. Okay. Eight meters per second and 50 degrees. So we can use the Suvat equation, S of y equals uyt plus half gt squared. So that's on the formula sheet, so don't worry if you forget it in the exam. S of y wait, no. This isn't the most appropriate. This isn't the most suitable formula for tackling this question. It would be something where you involve the final final vertical velocity, because we know that at the maximum height, it no longer will go up, right? The object will no longer start because it's reached the maximum velocity, right? The parabola stops and it starts going down. So we need something that involves the vertical velocity. Okay, so we can go to our formula sheet and we can kind of try and find that. Now, somewhere here, yeah, it is. What is the question asking for? Why? Okay, time. That's interesting. So maybe you have to actually just combine multiple. Yeah. Oh no, you wouldn't. Yeah, you wouldn't. Yeah, you just use Vy equals Uy slash GT, I suppose. Okay, I'll show you the formula. So this is the formula we're going to use. Pretty simple formula, so I don't know if it's actually the correct formula to use, actually. Not too sure. So the vertical velocity is going to be 0 at the maximum height. So we just sub in 0. We know the initial vertical velocity is 8. So it's the actual total magnitude of the initial velocity multiplied by sine of 50 degrees. And sine in this case relates to the vertical velocity. G is negative 9.8. That's on the formula sheet. And then we multiply that by t. So that's the equation we just wrote. And then we just solve for t. So we add 9.8t on both sides. We divide by 9.8. So goes over here. T equals 8 sine of 50 degrees over 9.8. I'm not too sure if this is the correct answer. It does not seem right for not a 9-mark question, a 4-mark question. Okay. So here is our time. So 8 sine 50 degrees. We are in degrees, just, you know, be wary of that in an exam situation. We divided it by the acceleration from gravity, which is 9.8, and then we got an answer of t equals 0.625. I think the question, yeah, two significant figures, so 0.63 seconds. I'm gonna check the marking for part A. Okay, it is correct. What? How's that 4 marks? Okay, I don't know. I'm not questioning it. I don't know. Okay. Anyways, we got that part right. Surprisingly. Yeah, to be honest, 4 marks for that is quite generous. Yeah. Okay. 6 marks for part B. Calculate the magnitude of the ball's final velocity when it enters the bucket. Show you working. Okay, so now we're involving the diagram, right? The diagram actually becomes a major factor to solving this question. So obviously we're given the initial vertical height that the ball is launched. And then we're given the height at which it lands, which is actually greater than its launch height. So we need to find the difference of that, which is our s of y. So obviously it's 3 meters at the impact height, and so we need to subtract 1.8. So then we get 1.2 meters, and that's positive. Okay. So I'm just gonna draw the diagram, but like change it up slightly. So rather than it starting 1.8 meters above the ground initially, I'm just gonna subtract 1.8 meters from the entire diagram and just assume that the ball is launched from the ground. So this angle is 50 degrees, that was given. And then it lands in a basket over here. Excellent drawing skills, I know. And that's 1 point of the ground. Okay, and we're trying to find out the final velocity. Okay, that's me. That's a lot of one my goats. Okay, thank you. We can just sub all this information into the into our Suvat equations. So first we can write s of y equals u of y times t plus half gt squared. So s of y we know is positive 1.2. I already explained briefly why it's 1.2. And from this diagram you can kind of deduce that the vertical displacement is positive 1.2 meters. It makes it a bit more clear than the diagram that was given in the question. Okay. U of y is just 8 sine 50 degrees. We're going to keep it as an exact value for now. Actually, no, this is... Okay. Again, I'm using the wrong formula. That's not as appropriate for this question. I think v of y squared equals u of y squared plus 2g s of y. Wait, that's... Is that... Yeah. Okay, let me just change the screen. That's one of the formulas given, so... Yeah, I should just look at the formula sheet, look, like, you know... Goodness me, I don't know what I'm doing. Okay. So, we're trying to determine the final vertical velocity. So, that's really what we should be using, to be honest. I don't know why I keep referring back to the S of Y formula. Okay. Also, if you didn't know already, my explanations aren't that good, so just bear that in mind. Okay. To get the final velocity? Ooh, okay, that changes things. So we need the final velocity, not just the final vertical velocity. So first we'll calculate the final vertical velocity. So we square root both sides. U of y, I already said earlier, it's 8 sine 50 degrees, and this is all squared. That's a square symbol right there. We add 2 times g, which is negative 9.8, and then the vertical displacement is 1.2. Okay. We can just put that in a calculator. So those should be the correct values I just put in. We aren't going to pay attention too much to this value. We're just going to write it down just to keep track of it. But when we calculate the magnitude of the final velocity, we're going to use the exact value. Okay. Okay, now we need to find v of x. So, here we go. V of x is just u of x. Okay. Oh, so we kind of... Okay. Fine, I think we do kind of need the S of y formula. Yeah, okay. Okay. So the reason why I'm saying that... Your explanation is better than anything Rhyme could come up with. What? Okay. Okay, I mean... Okay, thank you, I guess. I don't know. we have this, so I'm just going back to this equation. So we could use the quadratic formula to solve for t, or we could use our graphics calculator. Those are two viable methods. So we're just going to put in our graphics calculator, use our function, find the roots, and then see which one's valid and which one's invalid. Okay. So we're trying to find the solutions. So we're going to subtract 1.2 on both sides. And we're going to put this function into our graphics calculator. So 8 sine of 50 multiplied by x, which in this case would be t. Half of g is half of 9.8, or negative 9.8. And negative 9.8 halved is negative 4.9. X squared. And then minus 1.2. Okay, so we get two solutions that are actually they're both positive. I don't know what's happening in chat. I don't know what you guys are talking about. It's pretty confusing. Anyways, we get two solutions that are positive, and in terms of the context of the question, or in terms of what this graph actually represents, which is x, but in this case x represents time, both could be considered valid solutions. But we need to think about the question, and we need to look at the diagram to determine which one's invalid and which one doesn't represent the time at which the ball lands in the bucket or the basket, whatever it was. So there's one. So time, let's find the root. So it's 0.24 seconds, around about 0.24. So that precedes approximately 1 second, which means that the shorter time is actually invalid. The reason why is because if you look at the diagram, it reaches the height of the bucket over here, right? I'm assuming this, well, I mean, the angle is 50 degrees, so definitely past 1.2 meters. And then it's on its way down as it enters the bucket. So there's obviously gonna be two, just based off the diagram, we can deduce that there's gonna be two valid times. But obviously we calculated it, we got the 2 times. Now we're just refuting the lower time, right? Okay. So the thing is, since I used my graphics calculator and I got this root, I can't really write the exact value. So that's a bit unfortunate. Oh no, we have an intruder. Okay. T, I'm just gonna write down the value. So here's the value, just from the graphics calculator. That's the time at which the ball enters the basket or the bucket. So we can use that and use our other formula to get the final horizontal velocity. Yeah. So you wait. Wait. This is not. Oh my goodness. Okay, never mind. Okay, screw that. Screw that. Okay. Oh my goodness. This is physics, not a bodybuilding show. Okay. 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 What I just did over these like couple minutes, these past few minutes, it's literally irrelevant. Oh my goodness. Okay, but that's good. That's good. We learn. We learn. That's actually unbelievable. Okay. I mean, the lessons still matter, I suppose. So obviously, this doesn't actually matter in terms of the question, but for other questions, um, it's yeah, it's something to just keep in mind. Okay, so we know that since there's no acceleration in the horizontal direction, u of x is actually v of x, right? Assuming that air resistance is negligible. So we know what u of x is. It's just 8 times cosine of 50 degrees, and that's just v of x. Oh my goodness. Okay. Oof. I mean, yeah, to be honest, if it was use if we had to use this method, it would have probably been at least 8 marks. Um, Now we have v of x and we have v of y, so we just get the overall magnitude by doing the square root of the horizontal velocity component squared plus the vertical velocity component squared. So that's expressed like so. And then we sub in the values. I'll write it in green. So v of x is 8 cosine of 50 degrees, and we square this. And then v of y squared, it's just whatever's underneath this bracket. Not bracket, underneath the square root. Which is just 8 sine 50 degrees squared minus 2.4 times 9.8, which I just simplified this part here. Okay. Now we should have everything. Goodness me though, that was a bit of a time waster. Yeah. We took a little detour, but yeah, it should be fine. Okay, so I just typed in what I wrote. So square root of v of x squared, which was 8 cosine 50 degrees, and then we squared the entire thing. And then I'm adding v of y squared, which is just 8 sine 50 degrees all squared, subtracting 2.4 times 9.8, which I've put in the calculator. And then that gives us 6.36. Okay. Okay. So our answer is okay. It's two significant figures, so we need to round it to 6.4 meters per second. Oh wow, there's a lot of people. Goodness me. Um. Anyways, I'll change the scene. So let's see if I got it right. Huh. Since they rounded the value, it's slightly different. Oh, okay. Wait, what? Method 2 gives the same value that I got, which was 6.4 meters per second. So I'm assuming I'm correct. Yeah, it's just that for method 1, which is the method I used, they rounded the vertical component of the velocity, so that's why there's slight rounding errors between my answer and theirs. But everything is sweet. Everything is correct. Oh no. Okay, this question is not good. Okay. 5 mark question. I swear my teacher said there was no 5 mark questions where it was kind of like. I mean, this is a discuss question, so it's not. He's not wrong, I suppose. Um, Discuss the nature of light by describing evidence from 2 key experiments. Okay, immediately I'm thinking Young's double slit experiment. Um, that's that supports the wave nature of light. So I'm not going to write down my response for this. I'm just going to say the key points that I'm thinking, and then just see if I covered all the key points. Okay. So the wave nature of light can be explained through Young's double slit experiment. So I'm just brainstorming right now. And then the blackbody radiation graph also supports the nature of light, but not the wave nature of light, but rather the particle model of light. Okay, so immediately, 2 key experiments, the blackbody radiation. Oh wait, no, photoelectric effect. No, that seems like a better experiment. Um, so you have multiple choices here. Yeah, you have multiple choices because the blackbody radiation graph does explain like or does support the quantization or the quanta in which electrons exist as predicted by Bohr's model. So how like using the discrete energy packets, for the photons or for the electrons, it actually accurately predicts the observations for blackbody radiation, and it accurately the graph, helps fix the ultraviolet catastrophe thing. But in terms of like the photoelectric effect, I feel like I'm more I'm more confident in like explaining that and discussing why that provides evidence for the particle model of light. Okay, so when actually is it? So you have the photons that have energy, obviously, and then that energy is transferred to the electrons on the metallic surface. And then, depending on if there's sufficient energy within the photons, so like if the photons have a frequency much greater than the threshold frequency of the metallic surface or the material, then the electrons can become photoelectrons and potentially ionize if the energy of the photons are in surplus. Um, I think because like I have to relate it to the stationary states. So it's like how when the photons are absorbed by the electrons, or when they're absorbed by material, the material can only kind of emit specific wavelengths. But I don't think that relates to the experiment. I don't know. Either way, by suggesting that the the photons exist in these by suggesting that photons have like discrete energy packets, that explains the and that electrons exist in the discrete stationary states. It explains this specific emission spectra of materials and especially hydrogen. Um, yeah, I don't know, but Young's double slit experiment is definitely doable. Like you can discuss how you know rather than seeing two identical bands of light on the other surface, right? When the coherent light goes through the identical double slits, you know, you see, a lot of scattering, right? There's numerous light and dark bands across the surface, and then that demonstrates wave-like properties, wave-like characteristics, which is obviously diffraction and constructive and destructive interference, because the double slits in the experiment have a width comparable to the wavelength of the light, of the coherent light. And because of that, they create the wavelets at those slits, which then kind of rounds the light, or according to the wave model of light, that kind of helps explain the range of light and dark bands, because when the light waves round at the slits, they cross over and then interact through the constructive and destructive interference, which is okay. I think I'm waffling here, but let's just see the marking guide. Okay. Okay. Young's double slit experiment and blackbody radiation both provide evidence for the behavior of light. Okay, so this one, I mean, I did briefly mention the blackbody radiation thing, so I'd say I get 1 mark for that, but definitely 1 mark for Young's identifying Young's double slit experiment. Okay. Young's double slit experiment, the interference patterns formed as light passed through the two slits demonstrates the wave nature of light. Yeah, that I basically said that. I think I said it in too much detail, so I wasted time. In contrast, blackbody radiation demonstrates the quantized nature of light as electrons can only absorb or emit energy in discrete amounts. Um, I don't know. I think I said that somewhere. I think. I don't know if I said the last part. I don't know if I made that conclusive statement, how like light shares both wave and particle characteristics. I don't think I mentioned that myself a full confidence level thing. Okay, this is the last question. Goodness me. Um, the length of wire AB is placed. So we're dealing with magnetic fields. 6 marks. Okay, but split into two parts. AB, incomplete loop, sitting within a magnetic field as shown. It moves with a constant velocity of 40 meters per second, creating an induced EMF of 23 micro Microvolts. Okay. Determine the magnitude of the magnetic field strength experienced by the loop. Okay. Magnetic field strength, what do we know? It's B. Okay, what formulas can we use? Okay, I'll just write the formula down. It's EMF equals negative N over, well, not over, multiplied by the rate of change of magnetic flux. So, I don't know if this diagram is saying, like, assume, since, like, we can see it's a uniform magnetic field that's going into the page, but I don't know if 1.4 meters is meant to be, like, I don't know if this part, right, is meant to be a square right now. Like, I don't know if we can make that assumption. I'm not too sure. Either way. I'm just reading the messages right now. Um, what? Um, I'm not sure if I'll stream daily. I'm not sure. I might try, but yeah. Hmm. EMF level 5. What does that mean? I don't even know. Wait, what? Okay, I'm so confused. Okay. Anyways, 23 microvolts. Okay, so just in case we forget our prefixes, in the formula sheet, we're given access to the specific prefixes. So if you forget in the exam, you can just head on over to the near the back pages of the formula sheet. It gives you a list of the scientific notation. So in this case, mu corresponds to micro, which is 10 to the negative 6. Okay, so I'll write that down. Okay, n is just one, right? It's just one loop. So we just kind of ignore n. Yeah. Okay. I'll try to do a specialist stream. Yeah. Okay. Um, we know that magnetic flux is just equal to B times A times cosine of theta, I believe. What? I'm so confused. Okay. So the change in BA cosine theta, I believe cosine theta just corresponds to the angle that the wire makes with the magnetic field. In this case, it's 90 degrees. Wait, no. I think it's... No, no, no. No, no, no. It's the normal to the plane of the loop. And the angle between that and the magnetic field. Since the loop, um, since the loop is in the plane, right? It's like this. The normal to that is, into the page or out of the page, but that doesn't really matter because um, the magnetic field is going into the page, and whether or not, um, well, it's in the same direction, so theta is 0, so then cosine of 0 is 1. Okay, yeah. Okay. The change in time, I'm pretty sure that relates to the velocity. So we know that the magnetic field strength is a constant here, right? But the area is changing. Ooh. But at what rate? Wait. So 40 meters per second. Hmm. Part B is pretty simple. So it's, yeah. Okay. The change in time. Okay, well, we can just think about it like this. It's going to the right at 40 meters per second. So after 1 second, which would be just the change in time, so we can just remove, um, we can just remove the change in time because it's just 1, I suppose. Um, Negative 23 times 10 to the negative 6 equals, um, we can factor out b, because b doesn't change in this case. And then the final area minus the initial area. The initial area, I believe we can just assume to, so in this case, it's just a square, I think. And it's in meters, so that's the scientific, no, that's the SI unit. We don't need to make any unit conversions. So 1.4 squared, and the area final, after 1 second, it would have traveled 40 meters. So it would be 41.4 times 1.4. Okay. So 41.4 times 1.4 is 57.96. So I believe that's the correct way to do this. And the question's asking for the magnetic field strength, so we're actually going to divide this area difference, the change in area, on both sides to isolate B. So the final area is going to be 57.96, and then we subtract it with 1.4 squared, which is 1.96. And then we find the difference between those two numbers. I mean, we can do that tech-free, but yeah. Okay, so B then becomes negative 23 times 10 to the negative 6 over 56. We got an answer, I just don't know if it's right. So the negative, I believe we can just remove. I'm pretty sure we can remove it. I'm pretty sure it's just indicating direction. Yeah. I think. I'm not too sure. I'm also revising with you guys, so, you know, I can't be too certain. Okay, 23 over 56 times 10 to the negative 6. Which gives us value. I'll write it at the top of the page. 4.1 times 10 to the negative 7 Teslas. Okay, so that's in two significant figures, which is what is required. Okay. Draw a conclusion. So this is the last part. Draw a conclusion about the direction of the not the indicated, the induced current within the loop. Induced current. Okay. Okay, what happened? You increased the flux. We didn't increase the magnetic field. We increased the area, which then increased the amount of flux that the loop experienced. If it increased in this direction into the page, it's going to try and decrease it. So it's going to try and go out of the page, right? This is Lenz's law, okay? Out of the page. And I think we can use our right-hand rule for this. So in this case, our thumb represents the magnetic field, the induced current, and is the our 4 other fingers, and then our thumb is kind of like the induced magnetic field produced by the loop. So it's trying to oppose it. You know, it's kind of like in chemistry, Le Chatelier's principle, you know, in equilibrium systems. So it's trying to oppose the change. So it's going out of the page, right? Our fingers curl this way, so I think it will just be anti-clockwise in the loop. We actually got it right. Okay, I'm surprised. Anti-clockwise direction. Oh my goodness. Lenz's law, I did state that. Okay. Oh, nice. That's pretty good, pretty good. Okay. I mean, that seemed decent attempt, I guess. Yeah. Would that mean it increases or decreases the magnetic field strength? I don't think the magnetic field strength would change. I think in terms of perhaps the net magnetic field strength decreases because of the produced. Wait. I'm not too sure about that one. That's a good question. But all I know is that the magnetic flux that the loop experienced increase because of the increased area. Yeah. I actually don't know, to be honest. We'll have to ask Sir that one on Thursday or something. I don't know. Anyways, that was paper 2 done for physics. 2023. It didn't take a long time actually. What? I thought I went over time, but apparently I'm under time, which is surprising. The similarity between Lenz's law and Le Chatelier's is pretty cool. Yeah, it is pretty cool. Yeah. Since they kind of start with the same letters, it's pretty easy to remember. Alright, I'm going to sleep. Good luck. Yeah, thank you, Gabriel. Yeah. Good night, good night. I'll probably be going to sleep too. Yeah. Okay. Whew. That was a chill paper, I guess. Yeah. I don't know what else to say, but I'll try to um I'll try to go over specialists tomorrow, perhaps. Yeah. And that will involve a lot more working out than for physics because obviously it's maths. That's the whole point of the subject. But yeah, I'll try to explain complex unfamiliar questions to the best of my ability. I'm not sure if my explanation is very good, but yeah, hopefully it should be alright. Yep. Thank you, Juan. Oh, thank you. I appreciate it. Awesome. Yep. No, you're awesome. You guys are all awesome. Okay. Alright. Thank you, Juan. I love you. Okay. I love you too. I love you too. Okay. Good night, everyone.